All right, the last thing that we're going to do in virtual heat transfer is do an example problem. And I think this will be helpful to try to put this all together. The basic steps or general steps for solving a complex wall section are going to be the same regardless of how we're doing this. We're going to first determine the coordinate system that's most appropriate, whether that's Cartesian or cylindrical or spherical coordinates. We're then going to take our big ugly heat diffusion equation and simplify it here in step 2. Then we're going to determine what's happening at the surface and what boundary conditions we want to use. And then we're going to do some math. So let's see how this can work out with a complex wall section. So what we have, I'm going to sketch out a picture. We have a wall of thickness L. So maybe it looks like this and has some thickness here, L. It has a constant heat flux, Qx double prime, coming into one side. So this is Qx double prime. And at the other side, the temperature remains fixed at a constant temperature. So I'll draw it like this. I'll label that side as Ts. Heat is generated evenly throughout the wall section at a constant rate. So this is Q dot, how much heat is being generated. And what we want to do is determine the temperature profile inside of the wall section while it's at steady state. So heat's coming in at one side, being generated inside, and leaving at the right-hand side because that temperature is fixed at Ts. But I want to understand what's the temperature profile. It's coldest on one side and probably hotter and maybe looks something kind of like a curve, but let's see what that could look like. So our general steps first is to determine a coordinate system. And this is going to be, it's a wall, it's not a cylinder, it's not a sphere, so that's going to be easiest in Cartesian coordinates. So I'm just going to write down our big ugly equation. This is just the heat diffusion equation, d squared t dy squared plus d squared t dz squared plus q dot over rho Cp equals d temperature d time. All right, and remember, so these funky d's here are partial differentials because in the general case, we could have temperatures changing in x and y and z and time all together. It's not changing in just one of those at a time necessarily. All right, so now our second step is to simplify. So we're asked to just determine at steady state. So I'll switch colors. This first term can be canceled out, right? D temperature, d time equals 0 at steady state. So a common thing that we're going to do, because we're often going to do steady state stuff, eventually we'll get to non-steady state. This next term, density and heat capacity are just numbers. So what we're really asking is Q dot 0 or not 0. And in this case, we know we're actually told about heat being generated throughout the wall section. So unfortunately, or fortunately, Q dot is not 0. So we have to leave that one here. Now we have our coordinate system. So we have x and y and z. And what these individual terms are asking us is sort of in which directions do we expect there to be changes? Do we expect there to be changes in the temperature profile in the vertical direction in Y, from left to right in the X direction, or in the in and out of the page direction. And really, the in and out of the page direction and the up and down direction, both of those directions we expect nothing really to be happening. Heat's flowing in the X direction. That's where all the good stuff is happening. So d squared t dy squared and d squared t dz squared equals 0. So our changes are only in x, in that x dimension. So this guy and this guy both get killed off. And that makes our lives a little bit easier as we simplify it. As we start to simplify more problems, we'll get more used to it. You'll get better at it. But that's the basic approach. Now in our next step, we have our BCs, our boundary conditions. And this is what's happening at the surface. So I'll define this side as x equals 0. And then this side here is x equals length L, because that's the thickness of our system. So we have our first boundary condition is at x equals 0. And at this we have constant heat flux. Which gives us a fixed slope of our temperature. Again, we can look at the boundary condition video to see what this could be. This is now d temperature dx evaluated at that location, x equals 0. Our second boundary condition is at x equals L, and we have a constant temp. So in this case, our surface temp is fixed, so that means that the temperature at x equals L is equal to that fixed value Ts. All right, so now we've set up the problem, and now we can do some math. So we'll start with our now simplified differential equation. So that is alpha d squared t dx squared plus q dot over rho cp is equal to 0. We'll divide both sides by alpha, just to get rid of that alpha there. We can go d squared t dx squared equals plus q dot over k equals 0. Now we can think of this as d dx dt dx, that's kind of a helpful way to think about it, equals minus q dot over k. All right, so then what we can do is just multiply both sides by dx. So this feels wrong, but dx, right? Dx is just a little number. It's a number, it's just small. So if we multiply both sides by dx, now this dx cancels out that dx, and we no longer have any dx on that left side, but now we have it over there on the right-hand side. So now what we can do is integrate. So we have now dt dx equals minus q dot over k. dx, and we're going to integrate that right-hand side. So this is a pretty easy one to integrate because q is a constant and k is a constant. So I'm integrating a constant with respect to x. So I have dt dx equals minus q over k times x, but I have a constant of integration c1. So how I get rid of my constants of integration is I use my boundary conditions. So I'll use boundary condition 1. So what did boundary condition 1 say? Boundary condition 1 here said I actually know something about dt dx at this magical place called x equals 0. So I'm going to plug in a 0 for x and see that this all works out. So dt dx evaluated at x equals 0, right? This is my boundary condition, equals minus qs over k. That's my boundary condition. So that must be true. That's what my BC says. So all I need to do is take my equation up here and plug in a 0 for x, and then make sure that my constant is such that this equation, this boundary condition equation, is true. Right? This is how we use our boundary conditions. So I have dt dx equals minus q dot over k times 0, because I'm plugging in 0 for x, plus c1. Now I just need to take these two guys and reconcile them by selecting a value of c1. So what this means is minus qs double prime over k, that's what my boundary condition says, must be equal to 0 plus c1. That's what my heat diffusion equation says, evaluated at 0. So what this tells me is c1 has to equal just minus qs double prime over k. All right. Now we can go back to our math. So this is back to our differential equation. We have dt dx minus q, right, the heat generated over k, times x. And now we have a new value of a known value for c1. It's qs over k. All right, now I multiply both sides by dx and can integrate. So I'm going to move this, keep dt over there, and this right-hand side is all multiplied by dx, right? Just treat dx and dt as if they're really small numbers, and we'll just move them around, and now we can integrate. So this gives us the temperature, right? We're integrating both sides here. We'll integrate this in two parts. First, we'll integrate this first part, and then we can integrate the second part. The first part, this is minus q dot over 2k times x squared minus qs double prime over k x plus c2. Now what I have to do is use boundary condition 2 which is that the temperature at the other side at x equals L, the temperature at x equals L is equal to Ts. So I'm going to let you guys try to do that evaluation. Basically what you're going to do, right, is you're going to take this guy and plug an L there, plug an L there. And what T must equal in that case is Ts. So you're going to find C2 such that when you have TL here and L there and L there, that it all works, or TS here, L there and L there, that it all works out and gives you C2. If you want to double check your math, which maybe you do because this is one of your first times doing a complicated problem like this since probably math class, I'll write the answer down here. So you can double check your answer. We can also talk about this together. We'll do some more examples in class, but this is going to be T equals Ts plus Q dot over 2K. L squared minus X squared plus QS double prime over K L minus X. So that's what you should get after you evaluate for C2 and do a little bit of simplification. What this shows is just that the temperature profile is a parabola, right? We have an X squared and we also have an X. So what it means is it's a parabola that is not centered around the perfect center of our wall, but that it's actually shifted, in this case, a little bit toward that left-hand side where the heat is coming in. So hopefully this gives at least a little bit of a picture of how to think about and do these problems. There are some problems in the homework like this, and we'll also be doing some of these together in class when we're back in class together. All right, so that's all for this example for solving the heat diffusion equation.